Okay, so we're going to try something a little different today. I have a whiteboard. Hopefully this is going to work out a little bit better, less glare than the chalkboard, but we'll give it a try, see how it works out. So, we're going to take a look at a sample problem for dynamics, which deals with forces. Okay, I've got a scenario in which I am going to entertain and babysit my nephews for a while. And I think up a fun activity where they hop in little red wagons. Not drawn to scale. And I'd pull them. The two wagons will be tied together with a line. And I'm going to pull them, me, again, not to scale. And I'm going to pull with a force of pull. It's a type of normal force. I'm going to pull with 110 newtons. That's me sweating from the exertion. And sad face. And some hair. Poorly drawn hair. They're having a whole lot of fun. Let's find out how much fun they're having by finding out how quickly we're going to speed up. What's our acceleration in this case? Okay, well this one's a little complicated. So first I'm going to tell you that, like many of our problems, we are going to ignore friction. We'll say that I hit the wheel wells, the axles of our little red wagons, with a whole lot of very fine WD-40. And they slide very easily. So, no friction. Okay? So, at this point, we want to try and find out how much we're speeding up. What is our acceleration? Okay, well now we've drawn our picture, which is a good start. Next thing I'm going to do is I'm going to label my coordinate system. I'm going to go with our usual up being the plus y, and to the right being my plus x. Okay, so I've got that all set. Now I've got my coordinate system, I've got my picture, I've got some forces involved, and the forces are what's going to make all of this move. So, how do I deal with forces? Well, the best thing I can do is to draw some free body diagrams. So I'm going to draw free body diagrams over here. And this time it's a little bit different because I don't have just one object, I have two objects. And by objects, I mean nephews. In this case, I believe this one is Keegan, and this one is Brogan. Now, estimating their masses, I'm going to say that Brogan's mass is about 35 kilograms, and Keegan's mass sub K for Keegan, I'll put a B there, is about 20 kilograms. Okay, that's useful information. We need more than one free body diagram because we've got two objects here. So I'm going to start off and I'm going to draw a free body diagram for Keegan. And then over here, and just to make things more interesting, I'm going to draw, actually, I totally should have thought about that in advance. Keegan will be most upset if he sees that I give the color green to someone else. So Keegan's going to be green. He likes green. And Brogan, shamefully, I'm a terrible uncle. I can't remember what his favorite color is. So we're going to make him, let's go with blue. We've already got red on the wagons, so maybe blue will give us some good contrast. So I'm going to give a second free body diagram here for Brogan. Okay, let's start off taking a look at Keegan. We've got what force is acting on him. Well, we're most likely near the surface of the Earth because I, as a struggling teacher, do not have money to blast us off to the moon. So we've got our force of gravity, mg. We're probably physically on the ground because I'm not that irresponsible. And so we've got a normal force from the ground holding up the wagons. And in this case, because we're ignoring friction, about the only other force that we have is the tension in the wire right here that is pulling Keegan forward. Okay, so I've got his free body diagram taken care of. Let's take a look at Brogan. Alright, well, just like Keegan, he's got the force of gravity pulling him down. We've got a normal force holding him up. We've got the tension by Newton's third law going back the other way. And finally, he's got a rope that's attached to him that I'm pulling on. That's my force of pull. And we know that guy, or that force, it's equal to 110 newtons. Alright, so now we have our free body diagrams. So the next thing that we want to do is we want to find out from our forces, which we can see very clearly now, how they're going to accelerate. Because that's what we're interested in. We want to see how much they're speeding up, how much fun they are having. Okay. So I want to find out my acceleration. Well, as I recall, there's some sort of law pertaining to motion by some dead guy that relates forces and some of the kinematic stuff. It's what is it? Let me check my notes. Oh yeah, Newton's second law. Okay, Newton's second law says the sum of forces equals our mass times our acceleration, but remember, our force and our acceleration are both vectors. Well, when we add vectors, and you can check the vector videos, what we've done before is we split them up into two dimensions. We see what's happening in the x, so sum of forces in the x equals my mass times my acceleration in the x. The sum of forces in the y equals my mass times my acceleration in the y. Alright, so I'm going to get some more space and move over to the far side. I'm going to solve Keegan here in green, and then we'll take a look at Brogan in blue. So, if I take a look at my sum of forces in the x direction, because I usually like to look at the x direction first, for Keegan, I've got sum of forces in the x equals T, the tension. Is it positive or negative? Well, I take a look up at my coordinate axis up there, and it is positive x. Okay, so that's a plus. It's not a negative. Any other forces in the x direction? Well, I take a look at my free body diagram. Not on Keegan. So I'm going to set that equal to Keegan's mass times his acceleration in the x direction. Alright, now I'm going to take a look in the y, just to be thorough. We've got our y direction. Well, in the positive y, I have the normal force holding Keegan up, minus gravity, mg. That's going to be equal to mass of Keegan times his y acceleration. Okay? So now we've got a relationship for Keegan's Newton's second law, but it's probably not enough to find out what we want. We don't know our tension. We know Keegan's mass, so that's one thing, but we want to find our acceleration. We don't know our tension, so we can't solve for that right away. And down here, well, I'm not interested in the acceleration in the y direction. I'm interested in how much they're speeding up in the x direction, because that's the dimension they're having fun in. And I don't see any tension over here whatsoever. So my y direction's not giving me any information. So right now, I'm kind of stuck. Except, I've got another thing involved, right? And this thing happens to be my nephew named Brogan, so let's take a look at his sum of forces. His sum of forces in the x equals, well, in this case, the positive is going to be the force I'm pulling them with. And this time the tension is actually negative for him because it's pulling him back a little bit so that he's applying that same tension onto Keegan and pulling Keegan forward. And so I'm going to set that equal to the mass of Brogan, because that's who we're looking at right now, times our acceleration in the x direction. I'm going to take a look in the y, and I'm going to find that just like before, we had the normal force minus the mass of Brogan times gravity equals mass of Brogan times his acceleration in the y direction. And I realize now that I left a k off of this because we've got two different masses that we have to keep track of. All right. Okay, so we've got some more equations. This is good. We've got another equation where we have acceleration and our tension in it. That's helpful because with equations we can get relationships, and if we can get relationships, often we can solve problems. Okay, well, real quick, if we take a look in the y direction, we're ignoring friction because I used 3 cans of WD-40 on those wagons, so we are set. And we'll see that we know that the acceleration in the y direction is actually equal to 0 because the wagons aren't jumping up off the ground, even though that would probably be even more fun. And they're not sinking down into the ground, which I'm not certain that would be fun with the sheer terror and the screams and whatnot. But that's equal to 0. We see that whole term over here go to 0, and we know that our normal force is equal and opposite in these cases to our force of gravity. But we don't have any friction or anything else like that, so that information isn't helping us directly. What we do have is here. There, and, well, I have this marker out and ready. So, there. Okay, so I have two equations that I can play with. I'm going to switch back over to the black. Hopefully it's got better contrast. All right. So, I've got one equation from up here that tells me that my tension is equal to mass of Keegan times acceleration in the x. And I've got another equation that tells me that my... Oops! That is not the one I wanted. Sorry about that. You know, I put the stars right next to them. You'd think I'd be able to keep track of them. Okay, I've got another one that tells me that my pulling force that I am actually applying minus the tension equals mass of Brogan times acceleration in the x direction. Okay, well, so I got this from right up here. That's that guy. I got this from right up there. Well, now this one's a pretty good little setup because I've already got my tension is equal to something. Well, why don't I just plug that in down here? They're the same tension after all. Like I said, tension is the same throughout that wire, that rope. So it's the same force, the same value. One of them's going to the right. You can see here, that's a positive. And one of them's pointed back off to the left. That's a negative. Okay? So I'm going to plug my t equals mass of Keegan times the acceleration in the x in for t. So I've got force of pull minus mass of Keegan times acceleration in the x equals mass of Brogan times my acceleration in the x. I add my mass of Keegan times acceleration in the x. Let me get a better angle on this. To both sides. And I end up with, I'm not going out of frame, am I? Okay, no. I've got a little bit of room here, so I'm going to go with my force of pull equals mass of Keegan times acceleration in the x plus mass of Brogan times acceleration in the x. Okay. Well, I'm almost done. What I can do is I can factor out this acceleration in the x, and I end up with my force of pull equals the quantity of the mass of Keegan plus the mass of Brogan times acceleration in the x. I plug in my values. My force of pull is 110 newtons. My mass of Keegan is 20 kilograms. My mass of Brogan is 35 kilograms. And so I add these together. This comes up to 55 kilograms. I'm going to divide both sides by 55 kilograms. Am I going out of the frame yet? Almost. So I'll have 110 divided by 55 kilograms. And if you do the math, you'll find that our acceleration in the x direction equals 2 meters per second squared. Yay! Congratulations, folks. We have quantified fun. Fun happens about 2 meters per second squared. All right, let's check one final thing, because I'm worried that that wire that I have connecting the two wagons might break. Let me see what type of tension is going through it. Because if it's a really big number, then that line might snap. It could be like fishing line. I don't know. I have to use the stuff inside the garage. Okay, well, I know that my tension equals the mass of Keegan times the acceleration in the x. So now, taking that back over here, I've got tension equals mass of Keegan times acceleration in the x. Hopefully that's not too small. I realize now that it might be. Make that a little bit bigger. Mass of Keegan times acceleration in the x. Okay, I plug that in and I have my tension equals mass of Keegan was 20 kilograms. My acceleration in the x is 2 meters per second squared. I solve that and I find that my tension is 40 newtons. That's pretty low. I'm not too worried about that breaking. But if I start speeding up even more, or pulling even harder, then I might break that line. And then my sister would be very cross with me, what with the endangering the health and well-being of her child. So, we were able to solve for our acceleration of both of the boys, with me pulling them with a set amount of force. And we were also able to find the tension in between these two wagons. Now there's one thing that I kind of used and I didn't talk about specifically, but you'll notice that I didn't put an acceleration for just Keegan or an acceleration for just Brogan. And that's one of the things that I actually incorporate in a lot of this. They're tied together. And so normally when two things are connected like that, I always describe them as having their kinematic values locked. In other words, they have to, if one goes 1 meter, the other has to go 1 meter. If one is going 2 meters per second, then the other one has to go 2 meters per second, because if one's going faster than the other, then they're going to get further away. But they're tied together, so they can't get further away. And by the same token, if one speeds up, the other has to speed up the same amount. And so that's what we've used over here, where our accelerations are actually the same between them. So anytime you have two objects that are physically connected together like that, you're pretty safe in assuming that all of those values that we saw in kinematics, our displacement, our velocities, and our accelerations, they need to be the same at all points. Because if they're different, that means these two objects will be moving away from one another. Okay? So, hopefully that's a good example for you.